Hello, welcome to yet another problem solving session with Special Maths Academy. My name is Pius Honor, an instructor at Special Maths. Today we'll be looking at the second problem from the Nigerian team IMO selection test, year 2020. Alright, so the problem goes as follows. Given real numbers A, B, C, we define the mid of A, B, and C to be the sum minus the maximum minus the minimum. Okay, so we're to find all functions from f from rationals to rationals such that we have this equation for all xy rational. Okay, so first we have to understand what this mid entails. So this mid is actually basically the middle number if we should arrange these three numbers ABC in increasing order. So for instance, the mid of 2, 4, 5. Based on this will be 2 plus 4 plus 5, then minus the max minus the minimum. So this just means we cancel out the biggest and the smallest, so we're left with the middle term. Okay, so yeah, generally this mid may not necessarily be strictly in between the minimum and the maximum, so we could have instances where there are some repetitions, so something like this. So in this case, this would be based on this definition, it would just be 2. So even though 2 is equal to the minimum as well, it can still be the mid because of that repetition. And of course, if they're all equal, then it's still going to be the same number. Alright, so looking at this functional equation, it looks a bit strange, so we need to be able to handle this portion involving the mid, so we have to be careful about that. So we'll look at this special case we just mentioned, where it's easy to deduce what the mid is. So if we know any two among the three given terms are equal, then we can be sure that the two that are equal will be the mid. So we're going to take there are three possibilities if we want to pair them up. So we're going to take all possibilities and see what we get from that first. Alright, so the first one is a case y equal to 0. So in this case, we are basically just say set y equal to 0 in the equation, so called the star. Alright, so set this a star. Alright, so what we get here is f of minus this plus x minus f of 0 is equal to, so now we have minus 3 over 2, absolute value of the mid of 0, 0 and f of x. So 0 is going to be the mid of this, and so this is just simply equal to 0. So that's simplified the complicated portion. Now looking at this equation, there are lots of things we could actually do with this. So first of all, this implies that f is injective. That is, so suppose we have f of x equal to f of y, then from this expression we're going to have that f of x, making this subject in the above equation, that will be f of 0 minus x. In the same sense, this is equal to this, since f of x and f of y are equal, and then we get similar expression. So by equating the final two terms here, we get that x must be equal to y. So this means x equal to y. So it's injective, and also we see that it's surjective. So f is surjective. Alright, so to do this, it's even simpler. So we had this minus x. So by change of just a little bit of change of variable here, we'll get t. So this means that given any value of t, any rational value of t, then f of this whole expression here is going to give t, so f is subjective, meaning we can achieve every possible value by taking some f. Alright, so this, putting this together, this means that f is a bijection, so it's bijective. Okay, now that we know f is bijective, so we could do something a bit more. Now we're going to set in this equation, which I'll call plus, so we'll set x equal to 0 and plus. Okay, so while we're doing this is an attempt to find out some relationship between f of 0 and other terms, and possibly to find what f of 0 will be. Okay, so that will simplify this bit here. Right, so we get f of minus f of 0 plus 0 minus f of 0 is 0. So this means f of minus f of 0 is equal to f of 0. And since it's injective, it just basically means we can cancel out f. So like what we'll prove here is just similar to cancelling f and getting that x equal to y. So we're just going to do that here. And we have this. So f of 0 is 0. Alright, so meaning we can adjust our equation plus to get this. So this will be our new plus. Okay, so that was good. We could probably use this at some point later on, so just box this in. Now let's try something else. So we equated initially y equal to 0. Okay, so we'll try other options. So suppose f of x equal to 0. Okay, so based on what we just got from the fact that f is bijective and f of 0 is equal to 0, I'm not sure much will come out of that, but let's see how it goes. Okay, excuse me. Alright, so this time we are considering f of x equal to 0. So without proving the initial part, normally we can't just say this, so we have to say suppose f of x equal to 0, and then we plug that in. Okay, but in this case we can let f of x equal to 0 because f is a bijection. So we have so we set x to be equal to f inverse of 0. Alright, so this way we now have f of x is 0. Actually f inverse of x of 0 is just 0, so that's why this part may be unnecessary. So we have f of 0 is 0 as we had before. Okay, so if we do this, let's see what we get. So basically all we're just doing is setting x equal to 0, right? So we have so we are doing this in star. So we have this minus f of 0 plus 0 plus f of y is equal to mid of 0, y, and f of 0, which is just 0. So this is 0, this is 0, so all this is 0. Okay, and from here we get f of y and f of y, so everything just actually cancels out here, so nothing new, just checks out. Alright, so look at the last possibility, which is when y equals f of x. So in this case you can just start with f of x and set y equal to f of x. Okay, so if you do that, we have in the first portion, so this is t in star, so the portion here, we have just get 0 in there, so f of 0, that's the 0. Okay, so that means just get f of 0 plus x minus f of x is equal to minus 3 over 2 mid of 0 is now f of x and f of x. Okay, alright, so this is just 0, this is x, f of x, and this is minus 3 over 2 f of x. Alright, so we're going to try to reduce this a bit more, making use of what we had from plus. So remember that y is f of x, so if we plug this in plus, so this will imply f of minus y is equal to minus x. So it gives us a way of writing x in terms of y, so this minus f of minus y. Okay, so this is from plus. Okay, so we're going to use that now to rewrite this equation. So that becomes, instead of x we have f of this, a minus f of y is equal to minus 3 over 2y. And just rearranging the terms here now, so we have this. Okay, so you can call this equation 1. Probably useful, could use it at some point. Alright, so that's all for initial attempts on this. So you see that plus is quite handy. So what we're going to do now is we're going to rewrite equation star in a different way based on the idea we just used from plus here. So this transformation we did here, we're going to try to see how we can make use of that in the original equation. So we have f of y minus f of x plus x minus f of y, yeah, alright, equal to minus 3 over 2 mid of 0, y, and f of x. Okay, now so we're going to write so let z be minus f of x, then plus will give us that f of z is going to minus x, so this is very symmetric, so x is now minus z, f of z. So using that here, we can now rewrite every stuff in terms of y and z. So we have y plus z, then this is minus f of z minus f of y, and minus 3 over 2 mid of 0, y, and minus z. Okay, so writing this way, we get something that looks nice partially. So this is sort of couchy but with something attached. So if you can get rid of this, then it will be couchy, but definitely it's not going to be couchy everywhere, because this would not always be equal to 0. The bid here cannot always be equal to 0, so it depends on y and z, and so this f is definitely not couchy, but let's see what we can use this for. So this looks super important, so this equation, let's call it dot. And one thing to observe is starting from dot, we can go back to equation star just by the same transformation we did, as z equal to minus f of x, or x equal to minus f of z. That's because f is bijective. So using that information, together with plus, we can always get back to star. So this means star is equivalent to a combination of dot and plus. So we don't necessarily need to refer back to star itself again. We'll always make sure both plus and dot are satisfied. Okay, so now take there are three possibilities you're going to be considering, three general possibilities. Okay, or maybe more than that. So the first one is where y and z are both positive. So we are going to be ignoring 0, because if any of this is 0, it's definitely one of the cases we covered initially where there are some repetitions in the mid. So we'll assume that none of them is 0. So if they are both positive, then the mid is going to be 0, because it's going to lie between one of the positive, that's y, and the negative, which is minus z. So that way we've gotten rid of the extra term. So this is now Cauchy. To make this complete, we can include 0. That doesn't change anything. So we just do that, and we have this. So this means f is Cauchy. F is Cauchy on q greater than or equal to 0. And based on the Cauchy type equations, we know it's going to take the form. So we know this is going to be f of x is equal to f of 1 x for all x greater than or equal to 0. Okay, so yeah, that's that. And then now we look at a similar one when they are both negative. This time around y will be negative, but minus z will be positive. So once again the mid is 0. So this way we still have our Cauchy type equation. Okay, so f is Cauchy on q less than or equal to 0. So as a matter of fact, by bringing in maybe, let's say, a new function defined this way, we're able to change the domain of this restriction here to non-negative. So by doing that, it's just going to be similar to what we had before. It's going to take this linear form. So this means that f of x is actually going to be equal to f of minus 1 minus x, something like this. So okay, or if you go more directly, you can write it this way, or in this case x greater than or equal to 0. So that's if you go with this. Alright, so this means f is linear on the positive axis and also linear on the negative axis, but not necessarily with the same gradient. So it depends on f of 1 and f of minus 1. I know f is not entirely Cauchy, so there's a good chance that they are not equal. Okay, so we have, in summary, f of x is ax or bx for x greater than or equal to 0, and this for b x less than or equal to 0. Some a and b are rational. Okay, so now we have this form. So we're going to try to see if we can deduce what a and b must be, or what they have to satisfy. So we have two major options, dot and plus. Okay, so let's look at plus first. So here we call from plus we have f of minus f of x is minus x. Okay, so for x greater than or equal to 0, we can simplify this to be, we have minus ax is equal to minus x. So it depends on, we have two options here, so it depends on two things. So if a so certainly a cannot be 0, right? So a cannot be 0, otherwise we're going to have f of 0 is minus x for all x non-negative, so that's because, alright, so a is not 0, so it's either positive. If it's positive, then what's here will be negative, so this would be b times that, so minus abx. And so this, for this to be true, require ab to be equal to 1. And if a is less than 0, then minus ax will be positive, and this will be equal to a times this, so that's a squared x here. And so in this case, comparing coefficients, a squared must be equal to 1. And since a is less than 0, this particularly means a is equal to negative 1. So we have these two options. Okay, so we'll do something similar now for the negative ones. So this time minus f of x itself will be bx. Okay, so once again b is not 0, so we have two options. If b is bigger than 0, then minus bx will be negative, will be positive, since x is negative. So this, following this rule here, is equal to, so this is a times that, so minus abx. Alright, so comparing coefficients on this, we get this must be 1. And if b is less than 0, then similar to what we had before, this will be minus b squared x, and this means b squared is equal to 1, or b is equal to, since b is negative, minus 1. Okay, so we're going to summarize this as follows. So we have majorly two cases. So case, let's say case 1. AB is equal to 1. Okay, then case 2 would be when AB is not 1. So this will imply that A is not bigger than 0, and also B is not bigger than 0, otherwise we'll have AB equal to 1. So this means A is less than 0 and B is also less than 0, so A is equal to minus 1 and B is equal to minus 1. Okay, so for this case, this means f of x is just simply minus x, and this is Cauchy. So this definitely is going to fail when we plug it back in dots. So dot implies contradiction. So in fact, we only have one case, so we must have a b equal to 1. Alright, so okay, and from this, since and from this we get that both a and b will be positive, otherwise we have that they will both be negative since they multiply to a positive number, and that will still give what we had before. It doesn't work, right? So definitely they have to both be positive, and so they're just reciprocal, so b is 1 by a. Okay, so now that's for plus. Now look at dot. Let's see what we can get. And meanwhile for dot, we already had two cases, so if they are of the same sign, that's y and z. So what remains is to check the cases where y and z of different signs. So let's see. Okay, so we had this is dot f of y plus z is equal to f of y plus f of z minus 3 over 2 made of 0, y, and minus z. Okay, so now we look at when y, so when y is greater than 0 and z is less than 0. So when we have this, then in that case this will be positive, this will be positive. So the mid is just going to be the lesser one between y and minus z. So what we have here is y plus z could be positive, could be negative, so we don't know much about that. Now f of y, that's positive, so that would be ay, and f of z, that's negative, so that would be bz or z over a. So rather than this, I'm going to write what we have as. So here we have, remember they are both positive, so the middle will be the smaller among them, and taking absolute value, that's the positive. So we have this to be a minimum of y and minus z. Okay, so now just quickly take two cases. Okay, so we take two cases just quickly. So we have case 1. So if this is greater than or equal to 0, then we have that y is greater or equal to minus z, which is bigger than 0. So the minimum there is minus z, and since this is positive, what we end up getting is a times that, okay, ay z over a minus 3 over 2 minus z. So ay will cancel out, and striking out z, we're going to get a is equal to 1 over a plus 3 over 2. So this should be enough to determine a and then b. So after this, all we need to do is check that this works every time. Alright, so we have a squared equal to 1 plus 3 over 2a. So by inspection we could see that a equal to, I think a equal to minus half should do this, and a equal to 2 should do this. So I'm just going to write a factorization that works. So we have this. So this means a is equal to 2 or a is equal to minus half. Alright, but a must be positive. So we have a is 2, and then b, which is 1 over a, is half. So this means for this function to exist, you only have one option. So 2x for x greater or equal to 0, and half x for x less than or equal to 0. Okay. So just need to check this for the remaining ones, and then so that'll be it. Alright. Okay, so if this sum is less than 0, then this time y is less than minus z. Of course, it's greater than 0. So need, so this time we need f of y plus z, so that will be half of x, so that will be half y plus z, okay, equal to ay, which in this case is 2y plus c over 2. Now the minimum here is y, so that will be minus 3 over 2y, and yeah, this checks out. Okay, so look at this other case. Okay, so for this case here, f of y now is half y, f of z is 2z minus 3 over 2. Now y is negative this time, so change this up here. This negative, this will also be negative. So what we want is we want the middle one, so we want the biggest of this. For example, if we have minus 1 and minus 2, then minus 1 will be the choice. So we want the biggest of this, but in terms of absolute value, that will be the smallest one. So we want this to be the minimum of the absolute value of y and of minus z, of which is of z. So as a matter of fact, this is essentially the same as what we had here, just swapping z and y basically, so this will also work. Alright, so that brings us to the end of this problem solving